an ongoing discussion on the topic of the appropriate distance function to use when working with K-means. Remember that a distance function or a metric function in clustering is a mathematical function that defines the distance between two observations of the dataset. Formally, a distance function is a function f that accepts two arguments, observation 1, vector x, and observation 2, vector y, and that returns a non-negative real number that defines how far away the two observations are. The smaller the distance, the closer the two observations are, and the larger the distance, the farther apart. Strictly speaking, we often use as distance functions certain measures that output negative numbers and not non-negative real numbers. For example, the cosine distance outputs values in the range of -1 to 1, and it does not respect two typical properties of metric functions, the triangular inequality and the coincidence axiom. Nevertheless, the cosine similarity is an exception in the class of distance functions. Importantly, and regardless of the measure used, distance functions are essential because they provide a measure of similarity between two observations. This is useful in most clustering algorithms to decide how to group similar observations together. K-means is one of the most popular clustering algorithms. In fact, this is probably the first clustering algorithm that we learn when we study machine learning for the first time. It is therefore important to understand the problematic of distance functions for K-means and to try to avoid the pitfalls of using inappropriate distance functions with K-means. One common misconception is that K-means minimizes the Euclidean distance directly. Formally, the Euclidean distance is the following formula, assuming we have only two dimensions for vector x and vector y. For the other x and y points with more dimensions, let us say n dimensions, the formula complicates a bit, but the idea is the same. Each term under the root square represents a dimension, and we calculate the deviation of the two observations in that dimension. We do this for dimension 1, dimension 2, dimension 3, and so on until dimension n. We square all of these deviations, we add them, and then we apply the root square. For example, imagine you are located at the two-dimensional space at point 1, 1, and you want to decide if you move to location 2, 1 or -1, 0. To help you decide, you can use the Euclidean distance. You measure the Euclidean distance for the first possible location, which gives you 1, and when you calculate the second Euclidean distance, you obtain the square root of 5, which is around 2.2, which is larger than 1. So now you know that the first location is a closer spot. The Euclidean distance is important, but to be precise, what we minimize in the K-means is the sum of the square deviations within each cluster. Confused? Let us see this in detail. Consider that we have not only two, but several observations, x of 1, x of 2, to x of n, where each observation is a d-dimensional real vector. K-means clustering aims to partition the n observations into k sets, S1, S2 to Sk. The objective is to find the k sets that minimize the sum for all clusters of the squared deviations between the points of the cluster and the cluster centroid. The double vertical lines that you see here represent the Euclidean distance, but since the Euclidean distance is squared, we obtain the sum of squares only. So in the end, and in K-means, the optimization criteria is to minimize the total squared error between the training samples and their representative prototypes. The minimization of the sum of squares is therefore mathematically equivalent to minimize the squared Euclidean distance. Note that we even use the Euclidean distance formulation in the objective function. Of course, we could minimize the Euclidean distance in K-means instead, but this would be much slower because of the root square calculations. We should be careful when trying to minimize arbitrary other distances, which are not equivalent to deviation minimization. Let us try to see why K-means can fail with other distance functions. In K-means, we have two steps. We update the points assigned to the cluster, and we update the cluster centers. In the first step, we find the points that minimize the sum of squares between the point and the cluster centroid. The objective here is to minimize the sum of squares, as we have already discussed. In the second step, we update the cluster centers to the center of the newly assigned points. Note that here, when we calculate the mean, that is the arithmetic mean, we are in fact minimizing the sum of squares too. The mean is what we call a least squares estimator. Most distance functions, however, do not minimize the sum of squares. For example, when using the Pearson correlation distance, we are not optimizing the sum of squares. This makes K-means lose part of its meaning. Please note that you can use the K-means with other distance functions. However, the algorithm is only guaranteed to converge, even if to a local minimum, if both the centroid update step and the data points reassignment steps are done in the same n-dimensional Euclidean space. If we have two optimization steps, they should agree. Lastly, I think it is interesting to point out that there is one distance measure that can be converted to the Euclidean distance, and that is the cosine distance. This distance function works in such a way that if you use this measure in conjunction with K-means, you ought to get similar results. But what is cosine similarity? Cosine similarity is a measure of similarity between two non-zero vectors. It is calculated as the cosine of the angle between the two vectors. Importantly, the cosine similarity does not depend on the magnitudes of the vectors, but only on their angle. Imagine that you have a collection of documents. You can represent each document as an observation object by a termed frequency vector. For example, we see here that document 1 contains 5 instances of the word team, while hockey occurs 3 times. The word coach is absent from the entire document, as indicated by a count value of 0. As shown, the data can be highly sparse. And by sparse, I mean they have many 0 values. The traditional Euclidean distance does not work well for such sparse numerical data. Conceptually, cosine similarity or cosine distance computes the cosine of the angle between vectors x and y. A cosine value of 0 means that the two vectors are at 90 degrees to each other, they are orthogonal, and have no match. The closer the cosine value to 1, the smaller the angle and the greater the match between the two vectors. Now that we know more about cosine similarity, let us see again the relationship between the cosine distance and the Euclidean distance. Now, let's see what we can do departing from the sum of squares. Given n dimensions and two vectors, x and y, we can calculate the sum of squares for each dimension. Then we can simplify the formula. We then simplify the summations, turning them into a sum of sums. Now let us try to simplify this further. Wouldn't it not be nice to transform the first two terms into constants? If we deal with L2 normalized vectors, the first two terms equate to 1 each. L2 normalization is the technique that modifies the dataset values in such a way that in each row the sum of the squares will always be up to 1. Knowing that cosine distance equals this fraction, we can substitute the denominator by 1. Again, we do this because we know that we deal with normalized vectors. L2 normalized vectors, to be precise. We see that the Euclidean distance is related linearly to cosine similarity. Note that you must enforce L2 normalized vectors for the K-means to work with the cosine similarity. In summary, you can L2 normalize your data and then use regular K-means. And that is all for today. I hope you have enjoyed the lesson. Next video we will try to answer the question of how to initialize the centroids of K-means. Happy views and see you next video.